Who's Pascal Van Hentenryck. So he's a professor at Georgia Tech. He's also the A. Russell Chandler III Chair and professor in the H. Milton Stewart School of Industrial and Systems Engineering at the Georgia Institute of Technology and the Associate Chair for Innovation and Entrepreneurship. He also happens to be the director for the NSF Advanced Institute in Optimization and also the director of the Socially Aware Ability and Risk-Aware Market Clearance Lab. So Pascal has numerous titles, but I guess intuitively, he's an expert in operations research in AI. I've had a chance to meet him over many years, and he's very special in the sense that most people, specialize on one thing. Pascal is very broad in terms of his research. He's a team builder. He was also previously at Milton, where he led the team in optimization. He's doing the same thing now with the Advanced Institute at Georgia Tech. And his work has had a lot of impact in lots of application domains with the industry. So a lot of people talk about doing research that is impactful. Pascal is the prime example of this, and he will tell us about some of his work. Okay, so without any further ado, please go ahead.
Thank you, Pascal. This is way too kind, and that raised the expectation way too high for me. So thank you. So I'm going to talk about fusing AI and optimization for engineering application, and I'll talk about some of the things that we do in the Institute. So there is a lot of material, but what I hope to do is to get you excited on some of the topics and some of these combinations that is emerging between machine learning, AI, and optimization. So everybody knows that AI has got a lot of press, and the public is very aware of the latest achievements in AI, especially in computer vision and natural language processing. So I was saying that AI has got essentially massive achievements in computer vision, natural language processing, with a lot of impact on many industries. So what we are doing is actually trying to find out if we can have the same impact on a lot of engineering discipline, and this includes electrical and electrical engineering, power systems, healthcare engineering, civil engineering, manufacturing. A lot of these applications, a lot of these areas in engineering, I think could benefit significantly for these recent advances in AI as well. So this is what we're trying to do inside the NSF AI Institute. So this is the building in which we are located. We have the north wing of this building on the 12 floors. It's a building Midtown Atlanta, really nice. And the most interesting thing about this building is that we have the largest spiral staircase in the world. So at least we have a nice space. Hopefully we'll do nice research in the nice space. But this is the mission statement of the Institute. And NSF like those things, but I think this one is actually really meaningful. So what we are trying to do is to do things, in AI that AI and optimization independently cannot achieve. And by putting them together, we can hopefully achieve things that they cannot do. And I'll give you some examples today of the things that I think the two fields cannot achieve independently, and that by merging them, we can actually do. So this is how the Institute is organized, and this is going to be relevant for the rest of the talk. So we start from big societal or technological challenges in four areas that we selected. Power system, you're going to hear about this, logistic and supply chain, you'll hear about transportation, resilient and sustainable systems, and then manufacturing, especially circuit design. And then from there, we actually have a number of methodology thrusts that we are actually pursuing to actually, try to actually make significant breakthroughs in these societal challenges. Now, these are the two main pillars. The third one are industrial partners. I'm old enough that I want to work on real problems, not synthetic data and so on. And so when we work with partners, we try to work on the real problems that they have, so that we can have impact on what they are doing. So this is the boxes that we have been working on, and I'm going to talk about three of them today. I'm going to talk about optimization proxies, which is a lot of the things that my group is doing. Learning to optimize, which is also one of the things that we are doing in transportation. I'll talk also about end-to-end learning, and then a little bit about reinforcement learning, which isn't going to be in the context of learning to optimize. That's what I'm going to do today. So let me start by optimization proxies. And before I get there, I'm going to motivate, what we are going to do there and why this is important. So what you see there is MISO, the independent system operator. So this is MISO, the independent system operator, which runs the grid from New Orleans to Canada. And they currently have about 19% of renewable. And one of the things that they are trying to do is to move to about 32% in the next 8 years. And to do this, they have a lot of challenges based on the volatility of the systems, but also the fact that the load inside the system is much less predictable. And I will show you some figures in a moment. And finally, they are very worried about extreme events, and they have many of them, some of them every year inside the system. So this is a little bit how they are organized, and I'm going to give you a kind of a crash course in how these systems are operated, because this is very important, interesting on how you can actually manage them. So what you do is that the day before, you have what is called the unit commitment, and you decide which generators are going to be on for every one of the days in the next day. And then every 15 minutes, you run what is called a LAC, which is trying to see, hey, do we have enough for the next couple of hours? And then you have the real-time market where you just match the demand and the production. That's how these systems are organized. One of the things that my group likes to do is build digital twins for every one of the systems that we are working on. And so we build a digital twin of the entire MISO system. It's about 50,000 lines of code right now, just to reproduce what they do. You have this beautiful manual that we had to read. It's about 1,000 pages of things, and they don't describe everything. We had to discover a lot of interesting things. But once again, we have this unit commitment the day before, and then we have this frac, which is essentially replacing the bits that you have on the market by the forecast. This is very important because a lot of players are playing games on these markets. Then you have the LAC, as I told you, and then the real-time market. So we're going to come back to this later on because I'm going to show you what machine learning can do in some of these contexts. This is a visualization of the system on the French system. I can't show you MISO because this is critical infrastructure in the US, so I'm not allowed to show you anything. But I have the entire French system at the switch level. It's amazing. And this is how the system is moving. This is the 5 minutes market. And one of the things that I was very surprised, this is the reserves, what you have to procure to make sure that if something happens, you have enough energy. That's the actual energy that you see every 5 minutes. So you see the renewable energy in blue and yellow. And this is the night, so you don't see any sun anymore. This is the morning now. And so you can see that these things are changing very quickly. So this is a system that you essentially is running over time in real time, and you have to solve these systems in real time. The new reality is the volatility that I've told you. And what you see on the left-hand side, the right-hand side there is the kind of errors that MISO is doing in forecasting. It's like an order of magnitude more errors that they did a couple of years ago, based on the fact that you have all these solar panels behind the meter, and obviously the volatility of wind inside a system. The opportunity for machine learning is that these systems are evolving very slowly. You don't, change the grid very often, and most of the time, the load is resembling what happens, the previous days and so on. So you're solving all the time these optimization problems and these forecasting problems over and over again. So it's a big opportunity for machine learning. And the challenge, obviously, is that you're doing machine learning, but for a system which has very interesting physical and engineering constraints. It's not like computer vision where you don't, you have an image and you're trying to learn these images. Here you have to make sure that what you predict is going to satisfy these physical and engineering constraints. So in a sense, think about this as an empirical risk minimization under constraints. So before I go there, let me tell you a little bit about forecasting and uncertainty quantification, because this is going to be relevant. So this is also an area which is a really interesting. AI is having a big influence on that area because you need to essentially predict, thousands of time series at the same time. That's what we need to do for this power system. And you have to capture also the spatial and temporal, dependencies. So if you have wind farms at a particular point and another wind farms, let's say 200 kilometers away, and the wind is blowing that direction, you have some information that you need to capture about how the wind will be at that second wind farm in a couple of hours. So you have to capture this, and you have also to capture the long-term and the short-term dynamics. I'll show you some of this. And so what is happening here is that you have a lot of interesting techniques that are coming from AI, which are basically now used in forecasting, like deep autoregression model, temporal fusion transformer. I'll show you that in a moment. So this is one that I like a lot. We use that for wind farms right now. So this is a recurrent network where we predict essentially a distribution, the distributions of wind at every point in time, every 5 minutes or every 30 minutes or every hour. And so we are learning essentially the parameters of this distribution in this neural net. And so the MAD, this is a little bit of the MAD, this is the recurrent network there that you have to tune. And this is essentially the various distribution that we are learning. And they are independent. We are assuming that for the time series, they are somewhat independent, but they are fixed distribution. And so what the deep learning system is going to do is learn the parameters of the distributions using that recurrent network. And you will basically have a log likelihood loss function to actually make sure that you are as precise as possible. So let me show you one of the things that we are trying to do, which is important for us, and we are using also new techniques to do that, is actually making sure that the ground truth is always in your cone of prediction. We want to make sure that we capture the ground truth inside the scenarios that we are generating. So this is another thing that we do. This is what we are using for these temporal fusion transformers for solar and load prediction. This is some images of the load here. This is a good day for the load. We are basically predicting, 92% of the time we have the ground truth inside the scenario we are generating. And you can see that this load is varying over time in a significant fashion. This is wind. Wind is much more difficult to predict, but you can see that in this particular case, we still have this is after 7 hours, we still have, 80% precision, capturing the ground truth 80% of the time, which is kind of nice. But you can see that the scenarios are more diverse here. The distribution is, is creating a very nice set of scenarios. This is solar. I love solar because it's a roller coaster when I was a kid. So this is interesting, but this is actually very interesting to predict. We are very good in general to predict solar. This is 1 hour. It's going to be relevant later on in the talk. But in 1 hour, we are extremely precise. So this is load that you see there, net load. So this is load minus the renewable. And so you can see that we are very precise. This is sun and even the wind scenarios. When you predict 1 hour, we are really precise at this point. So we have done a lot of progress in that area. And this is very useful for seeding the optimization problems that we are doing. Another thing that I like in this field is that we are combining methods now from computational statistic, optimization, and AI. So we can generate massive number of scenarios like this, but when we optimize, we can't just not optimize over millions of scenarios, thousands of scenarios. So you have to actually optimize over hundreds of scenarios. And we have this technique from computational statistic, actually finding a set of scenarios that describe that distribution, almost as well as this, thousands of scenarios. And so basically that this is convex concave optimization to actually find the best set of scenarios that represent the distribution for a fixed number of scenarios. And then finally, one of the things that we do is also another optimization problem for actually bundling some of these time series together such that we can predict better. As you can see, when you start bundling together using some, for instance, variance or intermittency, we get a system which is much easier to predict. And it's also decreasing the dimension of the problem tremendously. So that's the kind of things that we do in forecasting, which are extremely useful. Now, let me talk about this fusion of AI and optimization in more detail now. And one of the things that you have in optimization is you start from input. So optimization can be seen as a mapping from input, to output. The input of the optimization problems, and then you output some decision, which generators you commit, or how much generations you have in any places in your network. And so one of the things that we have been doing is exploring the idea of replacing that optimization model by a machine learning model. And so, and this is actually pretty interesting because we don't have all these issues that you may have in other areas where you are trying to do prediction, because we have always the ground truth. We always have the optimization model. It may take a long time, but we have it. So we never have any problems of data. We can generate all the data that we want. But the challenge is, can you actually get a machine learning model which is precise enough to approximate very well these optimization problems? And so this is, for instance, an example of an optimization problem that we have to optimize. So this is, the visualization that you have seen on the French system is essentially something like this. Much more complicated. I will come back to that later on, but very similar to that. And so what you have as input is the load, what the demand for electricity, both real and reactive power. And what you output here is essentially the set points of the generator, how much they produce in terms of energy, real power, and what is the voltage set points. And one of the interesting things that you see here is that you have these physical constraints there. This is the physics. These are the Ohm's law and Kirchhoff laws. And then on top, you have the engineering constraints such that you don't damage the equipment. So we have to learn this thing, right? So you have to learn, if I give you some input, can you predict the output, very accurately? These are these optimization proxies. And this has been a very active area in power systems in the last couple of years. And so the key point is that you can view that as a kind of a empirical remediation under constraints. So you have your traditional loss function. You have this, optimization algorithm that you want to approximate. This is the neural net that you are trying to build. But you have also these constraints there, and that's what makes everything much more difficult. You need to satisfy these constraints, physical and engineering constraints. And obviously the loss function is the accuracy of your prediction for the set points of the generators. So how do you do that? What we do is we build these neural nets which capture, the physical laws inside. So we basically capture everything that we need on these physical laws such that you can actually represent them accurately. And then we do a Lagrangian relaxation. The first thing we do is that we do this violation-based relaxation. We take all these physical constraints, put them in the loss function, but making sure that we capture the violations of the constraints. And then the second thing that we're going to do, so this is what you do there. So you basically have your loss function, which is the accuracy, and then the violation of the constraints. And one of the things that you need to do is actually compute these multipliers that you are using inside that loss function. And this is where you have this very nice synergies between optimization and machine learning. Because these problems are very well understood in the optimization community. We can actually find the optimal multipliers when we have an optimization problems like that. And this is called Lagrangian duality. This is like the best form of duality that you can have for problems that are nonlinear or non-convex. And so if you know these parameters, this is the training that you have to do. But what you're trying to do is view this as an approximation, a lower bound on the best that you do. You're trying to find these multipliers that are maximizing the accuracy of this particular function. So we have a max optimization and a min optimization embedded in each other. And so this is typically how you compute Lagrangian duality, but we are translating this to machine learning now. And the way you can solve this is by using essentially a subgradient methods. So this can be solved. This training can be solved normally, and then you have a subgradient step to do this particular step, and you iterate these two things. This is the kind of accuracy that you can get. So this is on the part of the French system, high voltage French system, and what you can see is that the maximum errors is actually an order of magnitude better than if you don't use Lagrangian duality in this particular case. These are some of the accuracy of these methods, of these models. So what you see on these plots is you have the generators there, which are ordered by the amount of generation that they have. So this one is the most generation, this one is the least generation. So this is the generation of the generators. This is the scale of the generators. This is 1 gigawatt of power. What you see here is the L1 error, and you can see that the scale of this error is actually 4 orders of magnitude smaller. So these models are extremely precise. They can actually go to 10 minus 4 essentially in terms of the accuracy. Now there is one thing that that you have there is you have a regression task, right? And so this regression task is never going to satisfy all the constraints, even though we do use Lagrangian duality. So in practice, what we have is that we have another optimization problem, which is actually restoring feasibility at the end. So the proxy is really these combinations of machine learning and then a step of optimization, which is just restoring feasibility, assuming that you have something which is really close to an optimal and feasible solution. So I'll talk a little bit about that later on, because this is an interesting topic and a fundamental research topic in a sense. So let me tell you what we are doing under this RAMC project that we have with MISO. And so the problems that I describe is idealized. In reality, the problem is much more complicated. There are a massive number of inputs, the price point, the price curve of the generators, the bits, and so on. And this is the optimization models that they solve every 5 minutes. And so we build an optimization proxy for this, and we tried. And the first thing that we realized is that the commitment of the generators is actually very different for every hour of the day. So if you look at what is happening in January, almost every hour has a different set of generators which are committed. So it's like you are changing the topology of the network all the time. And so this is very difficult for machine learning, because now you are trying to learn this thing where the graph is actually changing. And so this is one of the difficulties that we had to overcome. And so the good news, however, is the fact that most of the generators are typically stuck at the upper bounds or lower bounds. And so if you could predict that, then the dimension of the problem is decreasing by about, a factor of 2. So you're fixing about 40% of the generators. So what we did is a completely different methodology. And so people who are doing pure AI will be completely, stunned by this, because we don't care about generalization here. So what we do is that we actually build just in time, just in real time, we build this machine learning model, which are dedicated to every hours of the day, so that we can train them fast enough and having the accuracy that we need. So we collect all the data the day before. This is how the systems are operated. As soon as we know the commitment of the generator, we generate all the data that we need. We train the machine learning model. And now we have a machine learning model for every hours of the day where we know the commitments. And this is how we can actually get the accuracy that we want. So we call that just-in-time learning pipeline. And we do that for almost everything now. So this is how we are actually using machine learning in this complex, engineering problem. Now, the actual machine learning model is a combination of a classifier and a regressor. The classifier is trying to find which generators are actually at the upper bounds and lower bound, and then the regressor is actually finding the rest of the generators. So the accuracy of this system is extremely high, as you can see. So this is the errors, the mean square error for the medium and the large generators, which is you're really, really close to an optimal solutions there. And this is, obviously it takes milliseconds to do that instead of the algorithm that has to operate in real time, which can take about 1 minute and 30 seconds. So we have a way to approximate this problem now with extremely high quality very, very quickly. This is the training times that they take. And you can see that as soon as you do this machine learning model for every hours of the day, it takes almost no time. Otherwise, you essentially have no time to train the machine learning model. It's going to take about 12 hours, which is essentially the time that you have. So one of the big things that we are doing in that particular space is using this for risk management. So this is a big topic. Risk awareness, resilience is a big topic both in energy system and supply chains in the US. And people don't really know how to do that in real time. And so this methodology can be used to do that. Now, the day before, you could run all these simulations, using the digital twin that we have and run a variety of scenarios. And you can have the risk assessment at that particular point. But what we are interested in doing is actually looking in real time what's going to happen, because now you have a much better forecast, which may be very different from what you had, like 12 or 24 hours before. And so what we do once again is that we build this machine learning proxy for the risk in real time, and we train them the day before, and then we evaluate them for every one of the hours of the day. And so using the updated forecast, that's kind of various scenarios that you can see. And these are the risk profile that we have. And one of the things, you're looking if you are, the right, operating cost, or if you're, violating some of the reserve that you need to have, or if you're shedding some load. And one of the things that you see in this plot is that it's actually quite interesting to see that we always identify risk. Sometimes you're not completely accurate. We are underestimating the risk. But this is an interesting tool to tell the operators, look at your system right now. There is a very significant risk that you don't have enough reserve. So it's not perfect, but at least we identify risk almost all the time in an accurate fashion. So there is more work to be done, but this is the first time that we know people can do really real-time risk assessment for this power system. This is the expected cost that you would get if you don't manage that risk properly. So I want to digress now and look at this thing more from I'm going to tell you two things. Okay, so how do we do this? How do we do this restoration phase? And then showing you something in supply chains which resemble that. So the one thing that you can do for restoring feasibility is to try to say, hey, I want to be very close to my projection, but no, I want to satisfy all my constraints. So you can do something like that. The problem is that sometimes that problem is as difficult as the original problem by the way the nonlinear solvers are working. So one of the very interesting research direction is how you restore feasibility when you know that you are really close to a solution, but you need the solver to actually be able to exploit that. So this is a very interesting research topic that we are pursuing. What you can do in power system is using techniques that are dedicated to that field, is power flow that restore the physics very, very quickly using those equations. And what you can see is that the kind of loss that we have in terms of the objective function is really, really small. So we lose a little bit when we do this, but we are really, really, really close to the optimal solutions, well within the market margin. So because none of these problems is really solved to optimality exactly. This is the same thing that we did for job shop scheduling. And so we had a dedicated architecture that was modeling the various parts of the problem. So, and this is one of the things that we do when we build this neural net. They typically capture the structure of the application. Here in this particular case, jobs and machines and so on. And then we have this the feasibility restoration, which is essentially a linear program, which can be done very, very fast. And so that's what we can use in that particular setting as well. And these are some of these results, and they were very surprising to me. So because this is a state-of-the-art solver, constraint programming is the state-of-the-art for this particular problem. And you can see that the machine learning model and the restoration is orders of magnitude faster and actually sometimes get even better solution than the state-of-the-art solver in milliseconds compared to the solver taking 30 minutes. So these combinations, again, of machine learning and optimization give you something that the solvers cannot do on their own right now. It's not always the case. So here, at some point, the solver is gonna beat the machine learning model and the rest of the feasibility restoration, but only after a long time. So this is the kind of things that we can do. Two key message there is that you have a very significant reduction. You improve very much on all the heuristic that people are using. And the other things which is very important is the fact that a dedicated learning architecture is super important there. If you use your traditional, multi-layers perceptron, you will not have many of the benefits of this dedicated architecture, which take into account the structure of the application in this particular scheduling problem. So, and that's the first part of the talk. So these optimization proxies. So what I'm going to do now is move to the second part, which is learning to optimize. And I'm going to completely change the field of application here. So what I'm going to talk about is a mobility system, which is another big area that I'm working on. And so what you are seeing here is a simulation of a mobility system for New York City, which is, you have about 50,000 requests every day, about 400 requests every 30 seconds. And so we are assuming here that we know we control every one of the vehicles, but we decrease the number of vehicles tremendously compared to what New York City has. And there is ride sharing, so you can share rides between different riders. So blue are basically the vehicles moving to our customers. This basic block there are basically the way the demand is located. And then you have this red curve where the vehicle is moving to a customer. So this is real-time ride sharing. So this is how we optimize this in practice. We batch some requests for 30 seconds. We get about 400 requests. Then we have an optimization model that solves that. At the same time, we batch the next generation of requests, and we keep solving this. So every 30 seconds, we solve an optimization model. How do we optimize? This is really a column generation problem. I won't go into the details, but what we do is we generate routes for every one of the vehicles, every one of the vehicles that can do sharing, and we minimize waiting time. So we want the waiting times to be as small as possible. We want to cover all the riders as possible. Now, in 30 seconds, sometimes you cannot optimize this such that you serve all the riders. And so what we do is we assign a penalty to the riders that have not been served, and that penalty increases over time, which guarantees that they will be served very quickly. So typically, before 10 minutes. And so this is the result, that we have. This is just to give you a baseline here. So New York City has about 12,000 vehicles. Here we have about 2,000. We serve everybody. That's a requirement of the system. We are completely fair. Everybody is going to be served. Nobody is dropped out of the system. And we have an average waiting time of about 3.56 minutes, which is, kind of remarkable. So I was super happy with this result, and then I made the mistake to actually ask to see how much the vehicles were idle. I asked that to my students, and this is the visualization that you're going to see. So blue are vehicles which are idle, and you can see that among these 2,000 vehicles, there is a massive amount of vehicles that are completely idle. They don't do anything, especially in the north and in the south of the city. And so the reason they are idle is that it's very costly to actually deploy a vehicle like this to something in the middle. That's going to increase the waiting time too much. And so basically you let them there because it doesn't matter. And so progressively they get idle because they get busy because they serve something here, and then they can move to the places where there is real demand. So we had to fix this. And so how are we going to fix the fact that we want all the vehicles to be highly utilized and trying to further decrease the waiting time? And so what we did build is building a model predictive control algorithm, which works at two levels. At one level, we have this real-time dispatching that you have seen. And then every 5 minutes or so, we have a relocation algorithm that's going to say, hey, what is the demand for the next, periods of time, and how best can I relocate the vehicle so that they are at the right place. And so that particular relocation algorithm is working at a coarser granularity. We discretize, the entire city into in a grid, and we have we forecast the demand for every one of these two zones inside the city. And we basically use a deep neural net for forecasting again. This is a distribution which is non-stationary, so it's not obvious. And then we have also optimization algorithm to do the zone rebalancing. We do that at the level of the fleet, and then we assign specific vehicles to move in the right places. So this is the optimization problems that we have. It's ugly. It's very difficult. It's very challenging. I won't go into all the details, but once again, you see these kinds of interesting constraints, which are flow balancing constraints, right? So you want to make sure that you don't lose any vehicles, you don't, invent new vehicles, and you serve everybody. So it's a multi-period optimization, and we again minimize waiting time, and then we also minimize the relocation miles that the miles that are needed for relocation. So the problem is that this mixed integer program is extremely difficult to solve, especially if you start having a large number of periods. So you can solve it nicely for 2, for 3, but after that, it becomes very difficult. And these periods of time, 10 minutes, 3 would be 30 minutes essentially. So what we did was building an optimization proxy for this. And so that optimization proxy learns the first decision, right? So it basically said, hey, I can use this deep neural net to predict which vehicles I need to relocate in the next period of time. And so one thing which was really interesting about this optimization proxy is that it could, in milliseconds, approximate what you can do for a model predictive control that would be using 6 periods. But that 6 periods, model predictive control cannot be used in real time, while the proxy can. And so it has essentially the same quality in terms of the waiting times. But now you can actually look at, about an hour instead of being able to look at only 20 minutes. So once again, this, combinations of optimization and machine learning can do something that you couldn't do before. Now, one of the things that we wonder is, can we do even better than this? What do you think? If I ask you, right? So the answer is yes. And so one of the things that the MPC is not very good at is actually capturing these long-term effects, these long-term dynamics. It's just, these 6 periods is much better than 2, but it's still an hour, and you don't capture the very long-term effect. And you also don't capture, how well these vehicles are, distributed for the next hour, for instance. And so what we want is that, we want to see if we can do better. And we have this, wonderful simulator that you have seen to actually predict what these vehicles are going to do. And so what we do is we can observe these particular trajectories, and we can use deep reinforcement learning to try to see if we can, improve that policy. And that policy now is not an optimization model, it's the proxy that we have learned. So we can differentiate that proxy, right? So this is cute, right? So what we did was actually putting some Gaussian noise around the actions that we are taking, the number of vehicles that we relocate at different places. So we have a lot of the different trajectories that we can observe, and then we can do policy gradient optimization for this. And so I'm skipping this, but essentially what we are doing there is typical things that you guys know in reinforcement learning. So no surprise, and we minimize the policy, which is going to be the reward being the waiting times for every one of the riders. So these are the results. So the interesting things is that on the waiting times, you don't change anything. These are the short-term dynamics. You don't improve the short-term dynamics. But what you do is that you improve the long-term dynamics, which are the relocation of the vehicles. So you have about a 10 to 15% reduction in the number of miles that the vehicles are traveling by capturing this long-term effect using reinforcement learning. So that was actually a very interesting results that we were very happy with. Let me move to the last application, which is also something that I think has a lot of potential. It's just the beginning of this exploration, but this is what we call end-to-end learning and optimization. A lot of the people now are calling this, decision-aware learning, and this is the idea of actually merging predictions and optimization. And so a lot of the things that you see in industry And this is, a lot of companies are doing their operations. They collect data, they do predictions, and then based on these predictions, they make decisions, right? So this is the typical things that people do. But when you look at this from an objective standpoint, objective function standpoint, the objective function of the machine learning model is completely different from what you want to do in the optimization models. And these two things are not necessarily aligned. You are trying to maximize the accuracy of your prediction there. And here you are trying to minimize cost or maximize revenue or whatever. But these two things are not necessarily aligned. You can have a very high precision here on something that you really don't care about in the optimization, or which has very limited influence on the optimization. And you can make large errors on something which actually is very important for your optimization. So the question is, can you do better than this? Can you actually take these things and put them in a single pipeline where you actually have both the prediction and the optimization inside a unique pipeline, and you can actually optimize both of them together? And that's what I want to discuss. There is a lot of work on this thing. I mean, these are early references, but this is an area which is becoming really, really active in merging these two, the prediction and the optimization together. So I'm going to show you this for an application is learning to rank. Think of it as you have a set of documents that you want to rank and present to a user. You have a set of, they are described by a set of features, and you want to present them in such a way that you maximize the utility of people looking at these documents, right? So I think you can guess what these kinds of applications are, right? There is one twist here, is that we want to also ensure some fairness in the way you show the documents. So you have a set of items that you want to rank. You have some attributes that are going to be protected. And you have obviously, for every one of them, the ground truth how much they are important for the user. And so that's what you want to do. Rank these items in a certain way, such that they are going to be relevant to the user, but you also want to be fair with respect to every one of the groups. And the definition of fairness here is that you want to expose every one of the groups in the same fashion. So the distribution of the utility function for the writers, for the users, is going to be the same for all the groups that it is for the entire population. That's what we are trying to do. So once again, what you have here is some form of empirical risk minimization with a particular constraint here, which is a fairness constraint. So how do we do this? So this is the traditional way you would do this. You would take all the items, you would approximate the relevant score of them, and then you would send that to the optimization model, which is a doubly stochastic model there that you can solve with a linear program. And then you can measure how much you have lost by the prediction and the optimization on the predictions that you have done. This is the optimization problems that you have. You want to make sure that you allocate every item to a position and that you have the group fairness over there. So what we did was actually putting all these things in a single pipeline. So you see the prediction there, but you also see the optimization inside the same pipeline. So the question is, how do you differentiate over this particular optimization problem? And there is some beautiful results in that area on how you can start differentiating about some forms of optimization problems. In this particular case, we used a result by Adam and Paul. Adam is in Columbia, Paul is in Berkeley, which they call, there are all kinds of names for this particular area now, but they call that smart predict and optimize. And essentially what you can do is, get a good approximation of the gradient in this particular case by solving two optimization problems. So by solving two optimization problems, every step of the training, you get a good estimation of a gradient, and you can essentially optimize everything together. And so the results are kind of very interesting, because not only you satisfy all these fairness constraints, but you also are much more accurate in the utility function for every one of the users is much higher than the state of the art, which use various forms of Lagrangian relaxation. So I'm gonna, since I have 5 more minutes here, I want to tell you a little bit about also decentralized learning and optimization, which is very important for a lot of applications on very large networks. And this is the concept of Lagrangian decomposition. How many of you know about Lagrangian decomposition? Okay, good. So you're going to see something really nice. So Lagrangian decomposition is one of my favorite techniques. So this is an optimization problem. And you have a problem because the two set of constraints maybe actually create tension between them. And so the magic trick in Lagrangian decomposition is that you remove this, you use a duplicate, a duplicate set of variables, and then you say that these two set of variables have to be equal. But what you do, obviously, is you use a Lagrangian relaxation for this particular set of constraints. And once you do that, you essentially decouple the problems in two steps. They're completely decomposed, and they may become much easier to solve. And then obviously you get the overall objective function by combining them. And then you can use Lagrangian duality, as I've shown you before, as I discussed before. And the beautiful thing is that, if this is your feasible region, this one for one set of constraints, the other one for the other one, what the Lagrangian decomposition does is actually reasoning about this subset of the region. So it's actually a very interesting technique. So how do we use that? We use that for the energy system. We use Lagrangian decomposition. We decompose part of the network. In France, for instance, there are 12 regions, so we decompose the problem in 12 regions. And obviously there are, some lines, some coupling lines, between these regions that we need to, take care of using the Lagrangian decomposition. If you look at, one of the difficulty here is that at prediction time, we don't know those flows. So even though you can optimize these things independently, you build a machine learning model for them, you don't know what is on the flows. So the way we overcome that is by using a two-step approach. We predict the coupling flows, and then we essentially solve all the regional system independently. And so using machine learning model, you train machine learning model for those as well. So you have a general machine learning model for the coupling flows and then one for every one of the regions. And the reason you can do that is because when you look at the coupling, the coupling is the coupling lines are an order of magnitude smaller. So the first stage there, learning the coupling flows is much easier than the rest of the system. So you can see this is on the various versions of the French system. And so these are the number of coupling flows there compared to the thousands of buses that the system has overall. And so the results here are really interesting because what you see on the top, the blue line is what the machine learning model is doing for one of the generators, the voltage magnitude of one of the generators, and then the real power there. The red line behind it is the ground truth, which is very nice, right? So the ground truth is really hidden behind the generators. The black line that you see there is actually the Lagrangian duality predictor that I've shown you before. So we have a very nice way when you decompose like this using Lagrangian decomposition and machine learning. We have a very nice way of capturing the nonlinear behavior of these generators in a more precise fashion. And that's how you can scale with very small errors for this very large network which has thousands of buses. So I think this idea we'd like to apply it to many different problems where you have multiple agents that are actually cooperating for solving problems. So you can have different machine learning model for every one of them. So final words. So one of the things that I tried to tell you at the beginning is that, can we actually fuse machine learning and AI and optimization and do more than the sum of the parts? And so I think I'd show you a couple of things where we can do this at this point. So these optimization proxies allow you to solve in real-time problems that you could not solve before. And you can solve them, really fast. In learning to optimize, what you can do is use both these optimization proxies but inside an algorithm. And then use simulation and reinforcement learning to capture very long-term dynamics. So I think this is actually something that we couldn't do with model predictive control alone. And so that's one of the things that I'm really excited about. And then this end-to-end learning is trying to merge the learning and the optimization pipeline. So this is, as I told you, what is called decision-aware learning. There are many more things to do. So these are the kind of applications that we are looking for. Design is probably the most difficult one. And this is happening all the time now when we have to design these networks from scratch or redesign them. But these are some of the things that we are trying to work on these days. When you deploy these things in practice, people will ask you for performance guarantee. Can you predict that you're really close to what you would do with an optimization model? This is not an easy problem. There are some really nice steps that have been done by some people in Denmark, but there is much more to do for scalability. Most of these systems have still operators, right? So they are operators looking at the decisions that you are recommending. And we have to find a way to actually tell them, hey, this plan, why are we doing this plan? If it's counterintuitive to what they have and their intuition is decreasing because of the volatility of the system, we have to actually try to explain what we are doing. So this is a very interesting thing. I told you about feasibility restoration. Self-supervised learning is actually also very interesting. So currently, we can generate massive amount of data, but it takes time to solve that. I mean, we have big clusters, but still, it would be nice to actually generate, find out exactly what you need to generate and do the learning and the generation on the fly. And then obviously, a lot of problems now are decentralized, and there is a lot more research to be done there. So that's what I wanted to tell you. Thank you very much for your attention. I'll be very happy to take any questions that you may have. Thank you.